Let's talk about latency. Latency is really important. I'll explain exactly what it is, but it kind of got triggered by this thread right here, which eventually went on into me making my own thread. But yeah, back to the square one. What is latency? Latency, and I like this little tool that Ben made. It's the distance between it's the time it takes for something to happen, usually in between servers or in between a server and a user, and it's usually measured in milliseconds. Kind of the way it works is that, let's say you have a user and you're trying to serve an API request or a page that's generated on the server, any sort of web app, right? When the user is in Kentucky or in Miami or whatever, and when the server is wherever the server is, right? And there's a certain distance to cross, and simply because of the way the world works, where you can't really travel faster than the speed of the internet, which can't really travel faster than the speed of light, and then there's a bunch of penalties because of our tech on top of that. There's only so fast something can really travel between 2 points on the internet. There are ways to make it faster, but usually there's a certain limit. So I like this map because it kind of shows, it's interesting, it shows the AWS data center latencies. So this means that if you had a server on the East Coast trying to talk to a server on the West Coast, how long would it take for the message to get across? This doesn't include any sort of processing time any of the servers spends to generate the response or the request or whatever it is. This is just the time it takes for it to travel, right? So say you have a server on the East Coast and the server on the West Coast, and they're trying to communicate about something. This is very common in microservices architectures. Yeah, that's 62 milliseconds for every trip. That's a lot. Or is this every round trip? I think it's every round trip. Either way, 62 milliseconds, right? But what if the other server, or in this case, you could also imagine this is a user. What if the other server or the user, the consumer of this API or the consumer of this resource, exists in Cape Town in Africa South 1? That's 200 milliseconds, right? So why this is a problem? Well, it's a kind of obvious why this is a problem, but the idea is that if it takes you more round, like if it's only one round trip, okay, fine, you can take 60 milliseconds. You might even be willing to take a 200 millisecond hit if your application or your system is not particularly latency sensitive, so it's not very critical that things get there fast. You might say, you know what, 200 milliseconds once, it's not a big deal, and that can be fine. But realistically speaking, it's not only going to be once, it's going to be a couple times. For example, in the context of web apps, which is kind of what I am good at, let's say you have a user talking to this. Every time he requests a new page, that's 200 milliseconds. Or let's say you have a more modern architecture, not a monolithic one, but a more modern one where you have a React app consuming an API. Your API lives here. The user now has the React app on their browser, so that doesn't have to get served again and again because it's static JavaScript. But every time they need any sort of data to populate the application, so they don't have spinners anymore, and I can show you an example of this right here. You can see you go on our website, and as soon as you hit any sort of page, you have loading spinners. Why? Well, I already have the app on my browser because I've downloaded the static files from a CDN, which is very close to me. So very low latency there. But anytime I need data, I need to go through basically a certain latency because I have to request data from the API. Some of this is faster, as you can see, because it's getting downloaded in the background and it's getting cached, and that can be really, really, really useful. So it hides latency. But as soon as you trigger new data, boom, you have to incur the cost. You have to look at the loading spinners, and you have to incur the latency cost, which can be a very, very real issue. Where was I? Right here. Okay. So you want to reduce latency as much as possible, and especially you want to reduce latency in the case where you have multiple round trips. Because for one page, okay, you might only need one API call, but you might need five API calls. I don't know. It depends, right? So this is why people out there invented serverless, which is basically, or not serverless, but on the edge. You've probably heard, oh, we're deploying on the edge with Vercel Edge or with whatever else is out there. And the idea is that serverless apps have basically the backend, the API, isn't anymore a one server living in New York, right? Nope. It's now basically a computational thing that where basically it exists on multiple servers all across the world, and it can be queried right here. So if that were the case, the user from Africa South downloads the React app from a CDN that is local to him, so very low latency. It can then request stuff from an API, from a function, from a serverless function, right? That is, on the edge right near him, so very low latency there. And he gets the one or two or three API requests that he needs. And that's the thing. Now he has the page. And you're thinking, wow, this is amazing. Why are we not using serverless and edge for everything? Because it's going to literally reduce all the latency and it's going to be amazing. And yeah, that's not exactly how it actually works out in practice. Because on paper, it's amazing. Because let me kind of explain this with a little bit of a drawing. Let me see. So you got user. Oh God, how let me make this bigger. Okay, you got I need this to be even bigger. You got the user, and then you got the app server, and then you also have data stores. Let me actually make these things smaller because now they're too big. Right? So, yes, you moved, when you had this thing in New York, you had it like this, where it was a lot of latency in here, in between the user and the app server. Now you moved this thing on edge, but your data store is still in New York. Your database is still in New York. And this is actually a much bigger problem. Having latency in between the app server and the data stores or the database is much worse than having latency between the app server and the user, because you usually do more queries when you do either page requests or API requests. So even if you have a modern app which uses like React on the front end and an API on the back end, or something like Next.js, which is kind of the same thing, realistically speaking, how many API requests will your page really make? Maybe two, maybe three. But then each API request might have multiple queries behind it, right? So this basically means that here what I was, you might have, the user requesting only once if it's a monolithic app, if it's server rendered, and so it's only one round trip because it's the one page and that's it. It comes with all of the data baked in. But even if you have like, as I said, a modern architecture with a front end that's client, it's the thick client, and then the back end is an API, okay, fine, you might have two round trips. Okay, that's not great. You will incur some latency because of having to do, as I said, multiple round trips again and again. So you will incur 400 milliseconds here, but I'd rather do it twice through the API request than do it literally a lot more times, because realistically speaking, in most cases, this is how it will look, because every single one of your API requests will most likely have multiple database queries or Redis queries. It depends on what sort of situation you have, how much you're caching things. But this is going to be a problem if your data store is still in New York, regardless of how great the edge network from Vercel or Cloudflare or whoever might be, if your data store is still here, this is a huge, huge, huge problem. You will incur even more latency using Edge than not using Edge, because back when the server was closer to the data stores, you actually incurred less latency overall, because each of these is 200 millis, like each of the round trips is 200 milliseconds. So this is 400 milliseconds. But when this was long, each of these was 200 milliseconds. So it was a lot more because it was 4 or 5 or 6 of them or 8 of them or whoever knows, right? Yeah, basic multiplication, right? The point is you want to remove latency. There are ways to do that. One of them is to replicate your database, right? Okay, so you have a database in US East 1, you have your edge server in Africa South 1, and your user in Africa South 1. Why not just also have your database there? Why not have multi, like this like in it might be natural to think that if we can have, you know, the compute or the app server distributed geographically across the whole world, why not the database? Well, this is the, I guess, the core problem that distributed systems as a discipline tries to fix and approach is how do you know, distribute data in a way that is consistent, atomic, persistent, the CAP theorem, maybe look into that. I'm not going to go into that. This is not the topic of today, but my kind of point is that distributing data is hard. It's actually very, very, very hard. You're either going to not have the data be consistent. So maybe, for example, you might have some rows in US East 1 that aren't in Africa South 1, or you know, you might have all sorts of other issues that come with the whole idea of distributing a data store. Again, I'm not going to go too deep into that, but the point is it's hard. And even if you go with like a simpler solution, like a master database and a bunch of read replicas, which will help you, but it will only help you on read actions, not on write actions. Every time your user in Africa needs to change anything, maybe his image, maybe his name or whatever, you have to incur the long latency again. Even though on read, it might be fast because the read replica is in Africa South 1 as well. For STEM applications, using this can work. But realistically speaking, my honest opinion is, why even find yourself in this situation? Why even put yourself in a world where you have to figure out a way to fix database to app server latency? Why not just keep your app server here? And now there's no latency almost between the app server and the data stores. And yes, there is more latency between the user and the app server, but you know what? It is what it is, right? Like, it is what it is. It's the way it is. There's no way about it. You can reduce this by using a monolithic app or like a server rendered app where you don't have a tick client and an API, because like the way we have it here, every time you go to a new page, again, you're gonna have to fetch different things from different API endpoints. If the pages were server rendered once with all the data baked into the HTML, then you only do one request, which is very fast, very amazing. You can also take advantage of stuff like preloading the pages. This is actually what we do a lot here, even though this is an API, or like a tick client and an API. We employ a lot of prefetching, we employ a lot of local caching to try to make this as fast as possible. So you can kind of see that it's still not that bad. But realistically speaking, the easier solution is to not even have an API and to just return the pages as they are. It's kind of a traditional way of doing web. People are not used to it anymore. Everybody likes to use React and Svelte and Vue nowadays. And that is fine. These sort of architectures do come with their own benefits and trade offs, but you have to be aware that when you have a thick client and an API, you will do more than one API request per page, which tends to result in more latency because you do more round trips. And going to the edge is not going to save you. In fact, it's going to fuck you even further for what it is. Um, Now, one interesting thing to kind of display this whole idea that I've made, and it kind of stemmed from this, Ben, who is also the creator of this thing, created this little animation right here. Let's go to it. It basically kind of shows you the latency in theory between different like AWS zones. So, for example, this would be if you were to travel any sort of data or information in between USE2 and AZ1. Am I reading this correctly? USE2, AZ3, USE2, AZ2. Let me see actually. Oh, okay, yeah. So the point is, this is a data center, this is a data center, this is another data center. Each of these like small gray circles is a data center. And if you try to communicate between an app server and a database, or between any two services, any two servers into anything in within the same data center, that's going to be pretty fast. 18 milliseconds, 70 milliseconds, 22 milliseconds, or actually, sorry about that, 0.22. But as soon as you try to communicate between different data centers, this becomes a problem. The latency, or maybe not the problem so far here, we're gonna see later when it becomes a problem. But the thing is, again, the further away two services are, or two things are, the bigger the latency. So as soon as you start to talk between data centers, you're looking at zero point 0.8 milliseconds, 1.13 milliseconds, 0.48 milliseconds, which isn't that bad, but this animation kind of displays the difference, and I think it's pretty cool. The thing is that this is between data centers which are really close to each other. They're all AZ1 or they're all US East 2, right? There's a good chance, again, that you might be communicating between data centers that are not as far away. Let's go back to the US. Let's imagine your database is in US East 1 and your edge server is in US West 1 and your user is in San Francisco, somewhere along the lines of here. I don't remember exactly where it is. Yeah, every time you do a database request, you're gonna have to incur this latency, which is not a fun thing. If you use an edge server, again, you could just use an application. You could just move your application server here and not do edge, and then you only have to incur this for the page generation or for the API request. I talked about this already. Sorry about reiterating that, but it's very interesting to see the latencies in real life. And for that, I've kind of made this application where, and you can kind of see the code. You can kind of see the code right here for the whole thing and how it works. The most important part is latency simulations, and particularly this core.go file. It's a pretty long file, but it kind of goes, it's basically the whole code that runs the simulations right here. And you can run them again and again if you want to. You can only run them one at a time. So if you guys click and somebody else already clicked, you can't do that. It doesn't do it concurrently. But it kind of tests what the latency is between different situations based on the distance between the app server, which in this case is in New York City 1 in DigitalOcean, and different locations for database. And you can kind of see I tried a SQLite database. I tried a same box Postgres, which means that the Postgres instance lives on the same server as the actual application, so on the same like VM. Then I also tried Intra AZ, which means it's within the same data center, a Postgres instance that is separate of the app server, but is within the same data center. So again, in New York City one. Then I tried inter AZ, which means that this app server is in NYC 1 and then the database server is in NYC 3 or 2, I don't quite remember. And then I tried inter-region, which basically in my case means the app server is in New York City 1 and the database server is in San Francisco, in SFO 2, I think. Again, all DigitalOcean. I use the same like processors and RAM and everything for each and every database. But it got quite interesting to where you can kind of see, oh wow, SQLite obviously is much lower latency than everything else. And that is because SQLite is in process. So it's like, it's kind of in the RAM, in the CPU with the app server, which makes the latency very, 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 very low. I think somebody had, I might be mistaken and I'm not gonna spend the time to search it, but Sam Rose has some pretty cool animations, and I think one of them shows what the latency is between like the CPU L1 to the L3 to the RAM, then to the database, then to the whatever. It's very interesting, but kind of what you get to notice here is, oh wow, well, SQLite is really, really, really low latency. And there's a whole article about this that they made. It's called, I think, N+1 or the N+1 problem on their website, SQLite. Very interesting, and it kind of explains the core benefit of SQLite, which is precisely this very low latency. So you don't really incur any sort of penalty from doing a lot of database requests. Same box Postgres is still pretty good, like 0.22 milliseconds, 0.40 milliseconds. The reality is that you could do even 10 requests per API or 10 queries per API or 10 queries per page generated or whatever. And it's going to be what, 5 milliseconds? That's not a big deal. Like 5 milliseconds, okay, in an ideal world, you would like to shave it off, but 5 milliseconds is not going to kill your application. It's other things that are going to be the bottleneck in this particular case. Honestly, even as you go, even inter AZ, okay, 2.5, 1.6, if you're trying to think what the fuck does read 1, read 2, and write 1 even mean, I have it over here in Core Go. You can kind of figure it out as you go through this, what sort of everything means, but it's just different, very simple. Okay, this is read 1. You select an ID, name, price from products, and ordered by price. Then this is read 2. It selects a product based on its name. And then this is the right one, which kind of inserts products. So these are not very complex queries. And also the database is seeded with only 1,000 products and then 10 reviews per product, something like that. Which means, again, we're not testing the actual database load or the speed of the database. We're simply testing like actual travel latency. As soon as you add more load onto the server and onto the database, these numbers will likely get worse. Maybe I'll test that someday. But strictly for travel latency, this is what you're looking at. And you can kind of see even in between like availability zones, that means having the app server, for example, in NYC 1 and then the database server in NYC 3, it's actually not that bad. Like even if you do, again, 10 queries, that's 25 milliseconds. It's not something you want to have, but it's not the end of the world. Of course, it can depend on different availability zones. So maybe DigitalOcean has the data centers closer to each other than other companies like AWS or GCP or whatever. But I mean, this kind of tells me that honestly, if you have your server in the same data center as the database, latency is not going to be the core problem. It might be someday, maybe, but for most applications, it's not going to be the core problem. This whole thing also obviously tells me, as I said earlier, that SQLite is pretty awesome in terms of its latency. It has its other drawbacks. I wrote an article about it on my elitesoftware.com blog, but that's a topic for another day. What is really interesting also is seeing inter-regions. So this is kind of goes back to what I was talking earlier about serverless and edge and how that can be a very real problem for your application. And like if your database is in New York and database in San Francisco, app server in New York. This is the case here. For a simple read, you're doing 67 milliseconds of latency, and potentially, for certain things, these are not even complex queries. 133 milliseconds of latency. This is bad. This is really bad. Because as soon as you have even free queries, this is what? 133.8 ms times free. It's 400 milliseconds. For an API request, if you have 2 or 3 API requests for your React API, for your React application for a single page, this becomes a huge problem. Users don't want the page to load in 400 milliseconds. Or again, once the database is under load, once the server is under load, this is going to get worse. There's also the aspect of what if API requests are dependent on each other. So you do an API request, get some data, then you do another API request to get further data on top of that, and now you have 800 milliseconds or potentially even 1 second or 2 seconds, and this is how your website gets slow. Again, latency is not the only bottleneck that you might have, but we're talking about latency right now. So this is a big problem, and this is the serverless problem exemplified directly. Now, this was still only New York to San Francisco. It can get worse. And I know that this particular one said 62 milliseconds. I don't really know why. Maybe AWS has a better system of infrastructure between the data centers, even if they're inter-region. I don't really know why this is the case. But look, man, 100 milliseconds between these two, that's a problem. And as soon as you start to serve users outside of the US, it becomes a real problem. And this is what, again, edge architecture comes with. Unless you replicate your database, which, as I've explained, it's hard, especially if you're talking about write replication and not just read replication. Yeah, but that's kind of what I wanted to outlay today. I guess there might be some sort of a conclusion to this. I like this image which I made. Do this round trip as few times as possible. That's kind of my point. Like, figure out what your architecture looks like and try to do as little distance as possible within the whole holistic view of generating the app or generating the page. There's maybe a few other things which I kind of wanted to touch on, but it's already 28 minutes in, so I'm not going to. Here are the servers I actually used, so you can kind of see they're all the same, their locations, and this is the app server. The app server was under relatively heavy load, so 90% plus CPU when it was processing or when it was simulating tests. And this is because it obviously has to do the app server work, but also the SQLite work and the Postgres work for the same box Postgres, whereas these only do the database work, and they had 30% load at best. So that's interesting as well. Which is to basically say that if you go out there and you start hosting your Postgres on the same box as your app server, you do win in terms of latency, but now you need a beefier server because it's all on the same server. So all of the work happens within the same box. Whereas if the database is separate within maybe the same data center, as I've said here, you don't incur that much latency, 1, maybe 2 milliseconds. But now the computational load is separate. So it's a different box with its own set of CPU and RAM and all that type of stuff, which can be good because it's kind of, in a sense, vertical scaling. Or was it horizontal? I always mistake those. But You know, I'm not saying go use SQLite just because the latency is a lot lower. It can be great, but also it comes with its own trade-offs, is what I'm trying to say. And part of that means that you need a beefier server, a beefier single box, basically. But also, hey, SQLite doesn't come with materialized views, which I like materialized views. I made a library somewhere here where I kind of tried to make some very rudimentary materialized views for SQLite, kind of a library, but I don't know if you should use it. It's not exactly the most up-to-date stuff or polished stuff. Anyway, that's about it with latency. Uh, Next time when you hear serverless and edge, you know what to do. Don't do it and cringe and tell everybody, look, latency is a problem. Point them to this video, like this video, subscribe to my shit. Also, I have a lot of interviews that I do with amazing people, very interesting, very smart people. Go check those out as well. Thank you. See you around.